Does one AI prompt consume an entire bottle of water? Or is it closer to 5 drops? Both numbers have been published, one by academic researchers, the other by Google, and the gap tells us something important. The question itself is broken. Artificial intelligence does use water, but there is no universal amount hiding behind every prompt. The real footprint depends on the model, the hardware, the location, the cooling system, the electricity grid, and even the time of day. The water problem behind AI is not really about a bottle. It is about the pipe. Every AI response begins as electricity moving through silicon. Almost all of that electricity eventually becomes heat. 8 small scale. A fan can move the heat into a room. At data center scale, thousands of high-powered accelerators can turn one building into an industrial furnace. Some facilities use outside air. Some use closed-loop liquid systems. Others use cooling towers where evaporation carries heat away. Evaporative cooling can save electricity, but some of the water leaves the local system as vapor. And that is only the water used on site. The power plants feeding the data center may consume water too. Researchers therefore separate the footprint into 2 layers: direct water at the facility and indirect water associated with generating its electricity. For the year 2023, all data centers in the United States, not AI alone, directly consumed an estimated 66 billion liters of water. Their electricity use was associated with nearly 800 billion liters of additional indirect water consumption. Those estimates come from Berkeley Lab. The indirect figure uses regional grid averages and cannot perfectly represent every company's power contracts. But the scale is still revealing. Count only the cooling tower and you miss most of the estimated footprint. Assign the entire data center industry to AI and you exaggerate it. AI is changing the shape of the system. However, Berkeley Lab estimates that GPU-accelerated AI servers used more than 40 terawatt-hours of electricity in 2023. Daii's scenarios suggest that United States data centers could consume between 6.7 and 12% of the nation's electricity by 2028. More compute means more heat and a harder trade-off between water, electricity, and cost. In 2023, researchers at the University of California, Riverside modeled the water consumed by artificial intelligence systems. Their estimate suggested that a conversation of roughly 20 to 50 GPT-3 queries could use about half a liter of water. That became the famous bottle of water headline. But it was not a universal meter attached to ChatGPT. It depended on assumptions about older hardware, cooling, electricity, generation, geography, and workload. In 2025, Google published a very different number. It estimated that the median prompt in the Gemini app used 0.26 milliliters of water, about 5 drops. Google's number was a point-in-time measurement of its own system in May 2025. The company also said that the figure had not been independently verified. It does not describe every model, prompt, or data center. So, which number is correct? Each may be reasonable inside the system and assumptions it describes. Neither should be stamped onto every artificial intelligence answer. There is another water-intensive building hidden behind the data center, the semiconductor fab. Artificial intelligence chips begin as silicon wafers and pass through hundreds of manufacturing steps. Between many of those steps, wafers are cleaned with ultra-pure water. Even tiny contamination can ruin microscopic circuits. In 2024, TSMC reported total water use of 129 million cubic meters across its fabs in Taiwan and its subsidiaries. That is the company's entire semiconductor production footprint, not the footprint of artificial intelligence chips alone. But it reveals the industrial scale behind the hardware. TSMC is also expanding reclaimed water use in southern Taiwan. By the end of 2024, its Tainan fabs had used more than 19.65 million cubic meters of reclaimed water, reducing their dependence on city water. The water footprint of artificial intelligence, therefore, begins before a server is switched on. Some of it is embedded in the factories that make the accelerators. A liter of water does not have the same impact everywhere. Using reclaimed wastewater in a cool, water-abundant region is different from drawing drinking water during a drought. Annual averages can also hide the hardest engineering problem: peak demand. On the hottest day, cooling systems may need the most water when communities and power grids are already under stress. A scenario study published in 2026 by UC Riverside and Caltech asked what would happen if water use intensity from 2024 did not improve. It estimated that new United States data centers could require between 697 million and 1.45 billion gallons of additional peak water delivery capacity every 24 hours by 2030. That is not a prediction that this much water will be consumed every day. It is a scenario for how much pipe capacity public systems might need during peaks. This is how a small average per prompt can coexist with a large infrastructure problem. Billions of small requests arrive unevenly in specific places through physical pipes with finite capacity. The obvious answer is to stop evaporating water for cooling. Microsoft says a new data center design for AI workloads can operate with zero water evaporation for cooling, avoiding an estimated 125 million liters per facility each year. But there is no free cooling system. Dry cooling can require more electricity, especially in hot weather. Moving the burden from the water network to the power grid may solve one constraint while worsening another. The better solutions are local. Use reclaimed or non-potable water where possible. Match the cooling system to the climate. Schedule flexible training jobs for cooler hours or better locations. Build cleaner electricity supplies with lower water intensity. Report peak demand, not only annual totals. And place new facilities where both the grid and the watershed can support them. Efficiency matters too. Google says the energy footprint of its median Gemini text prompt fell 33-fold in 1 year. Better chips, models, utilization, and cooling can reduce the footprint of each answer, even while total demand continues to grow. So, does your AI prompt consume 5 drops or a bottle? That is the wrong question. The honest answer is a chain. Which model? On what hardware? In which data center? At what time? Cooled by what system? Powered by which grid? Built from chips made in which fab? Artificial intelligence may feel like software, but its limits are increasingly physical: electricity, land, silicon, and water. The companies that win the artificial intelligence race will not simply be the ones with the smartest models. They may be the ones that can build the hidden systems beneath them without draining the communities around them.